Hi there, Calc AB students. If you don't know me yet, I'm Mr. Ray. I'm one of the calculus teachers here at Olympia High School. And I'm going to be working with Ms. Hoagie. And so you may see me on some of these videos. You may see Ms. Hoagie on some of these videos. And we may even have some other videos that we bring in from time to time from other teachers or professors around the country. The idea, I guess, with distance learning for calculus is that we will have a few videos each week that will cover some basic instruction for the material for that week. And then when we meet in our online Zoom classes, you'll get a chance to interact with one another and your teacher so that you can ask questions and then work on some examples and homework together. The model I like to think of a lot of times is the old teaching model, but it seems to work really well in calculus, is where I do a couple problems, we do some problems together, and then eventually you do those problems on your own for your homework. And we'll kind of work on that model, at least to begin with here a little bit, and see how it goes. There's be more interactive things as we get further down the road, I think. But for this first part, we're going to actually start in chapter P of your textbook, which is the preparations for calculus chapter. I like to think of it as prerequisite material. It's stuff from pre-calc, but I don't mean like pre-calc like last year's class. I mean like the pre-calculus mathematics that you've been working on pretty much your entire mathematics career to this point. This week's topic is a little different than last week. When we started class last week, you started with the idea of what is calculus. And now we're going to kind of prepare you for that study of things that are moving or changing. And in order to do that, we have to review a few ideas from your pre-calculus mathematics. And so if you have your textbook, go ahead and grab that. We're actually going to start right up in section P1, which is graphs and models. And I really just want to focus in today on graphs of functions and families of functions, and a few features that we look for in functions. And then the second part, we're going to focus in on linear specific stuff. So we'll be taking a look at both sections P1 and P2 today. So without further ado, we'll start our review. And we're going to be looking at a couple of different kinds of functions today. So I have my whiteboard here, and the title for today's material, I guess, we're gonna call this being is fun, families of functions, and then we're gonna look at the different types, and we're gonna take a look at some characteristics of those families of functions. So to start off with, real quickly, I know that a lot of you really like when we write equations, you know, when we write y equals, right? So if I start with the most elementary of functions, y equals some constant, let's just say 7, okay? We probably in calculus will use y equals a fair bit, but we also know that there's some function notation, f of x equals 7. So just a quick reminder that those mean the same thing. They're not exactly interchangeable, especially for those of you who are going to take the College Board exam. If they name the function f of x, then you should probably use that notation throughout the problem. If they name the problem y, then you should feel free to use the y notation throughout the problem. But if you want to interchange them, then you're going to have to do a little extra work and write out something like y equals f of x. So. Okay, these are a couple of constant functions. And as we know, when we look at the graph of a family of function, or not a family, of a specific function right now, okay, the graph is simply a visual representation, usually in the xy plane, the Cartesian plane, that represents what happens when you put an input into it. And remember, we call that domain. And then you get the output number, we call that range. And they represent it in some kind of ordered pair. So for our basic constant function that I've given you here, it doesn't matter what the input is. Every single ordered pair that's on this particular function, doesn't matter what we input for x, the y coordinate is always going to be 7. So I think maybe you're familiar with the T-chart way to come up with your functions. And it doesn't matter what you put in for X, you get a 7 every single time. And so that graph then that we make, that representation of this function in the XY plane, well, it's pretty boring, truth be told, because it's just a horizontal line, right? So if we look at the XY plane, we simply mark off to where we get y equals 7, 1, 2, 3, 4, 5, 6, 7, and we draw in our horizontal line, because no matter what X is, we always have a Y coordinate of 7. Oops, wouldn't you know it, I just missed the darn 7. There we go. And there it is. So a few ideas right there represented by this constant function. Just a reminder about graphs, that it's a way to show domain and range very quickly, because there's infinitely many points that make this a true equation. So it's nice to have a graph that will then illustrate that for us, so that we can see what does this function tend to be doing. All right. Let's talk about a different function in the family of functions, the linear functions. Now, if I were to ask you what a linear equation is, most of you would probably say y equals mx. Oops, lost my little tool there. Mx plus b, and that's a great way to think about it. We'll talk a little bit more in depth about linear later. In this case, remembering that, of course, the m was representing a slope, and the b represented something called a y-intercept. And intercepts are going to be a topic that we're going to talk about here in a little bit. The nice thing about intercepts are they make pretty easy points to find for your function. And sometimes they're the points that we are most interested in. So we'll be talking a little bit more about intercepts in just a little bit. Linear functions, of course, have straight lines for their graphs, represented on the XY plane. Usually, the previous one was, of course, a linear function. It was, like I said, it's kind of one of the boring ones, because it's just y equals a constant value. But then if we, oh, my line just disappeared. How about that? Huh. All right, we'll try another x-axis. There we go. In this case, I'm just going to draw a quick linear equation on here, something like this. And so the input and output pairs would all lie along this red line. The x coordinate, again, being what you put in, the y coordinate being what you get out, domain and range. But there's lots of different functions out there. And so one of the things that we want to remind you of in some of the work that you did in your pre-calculus mathematics was you dealt with some other polynomial functions. And you might remember polynomial functions means that we have a string of monomials usually added together, or if the coefficient is negative, it's subtraction. This one here, that's supposed to be squared. Boy, need to get practiced up on my writing here on the computer. So this is a quadratic polynomial function. I think some of you probably got into cubic functions and even higher ordered functions than that. You would have gotten comfortable with pretty much all the different polynomials and some of the fun things that we were able to do with those, especially thinking back to like your Algebra 2 days when you were first dealing with the fundamental theorem of algebra, like how many zeros does it have? You've got to count real zeros and imaginary zeros, repeated zeros, but that degree of the function always matched up with that. But again, there's more to the classes of functions than just these. That we're going to deal with in calculus. We're not going to stop there. The polynomials are great, and I love polynomial functions. Don't get me wrong, but we deal with stuff that functions in a more complicated fashion sometimes. So we need to be aware of what those look like too. So I'll start with a graph this time. Some of you have probably seen, oh, The x's are blue this time. Sorry, forgot to change them. Some of you have probably seen graphs that will look more like this. And you know that that's an exponential function. And we will be getting into exponential functions a little bit later in the year. Let me grab the blue pen again here. And the thing with exponential functions, okay, they're of a different form. In this case, they have a base number and the input is in the exponent for that base. And there's sometimes this coefficient a out there. And so when we see exponential functions, we might see a function that goes like this. That would be, for those of you who are really sharp and remember, that would be exponential growth. Because we did deal with both exponential growth and we dealt with exponential decay problems before as well. If I were to draw a quick exponential decay function, of course, it just flips it around and it goes the other direction. But we'll draw it anyway, just because we want to start high and then it decays and it slows down and gets closer and closer to the closer and closer to the x-axis. Boy, my curve was terrible on that one. I apologize. Those are some of the types of functions that we did a lot of work with. The last one that everybody really enjoys so much was the logarithmic function. And we know that logarithm functions, now they're a little bit different because they don't go into the negatives usually. Okay, they stay in the positives, and they'll look something like this. And so that's a logarithmic function, and we will be dealing with logarithmic functions, not for a while. So yeah, that's not till chapter 5. Oops, I clicked the button. The log functions. Yeah, this won't be until chapter 5 when we get into these, but we will be looking at the calculus of these functions as well. They typically look like this. We have the log some base number in the function like so, and we'll see when we deal with the logarithm functions that a few things do change up a little bit when we start dealing with the calculus of those ones, because they're kind of interesting. All right. Just a quick aside, it's really weird to be doing this just as a video, because normally I would say, okay, do we have any questions at that time? So pause there for a moment on accident. That's just second nature for me to just double check with everybody. So, all right. So I talked a little bit about intercepts earlier, and so the idea behind intercepts, your graph will have two kinds of intercepts, right? It'll have the y-intercept. Shoot, lost my tool again. Y-intercepts, and that's where the graph crosses the y-axis. Oops, crosses cross E. Oh boy. I'm going to leave these mistakes in here for this one. This one's kind of funny. The y-axis. Sometimes I'll be using some editing software to take out the really big whoopsies, but that one was pretty funny. Graph crosses y-axis, and it's actually, it's good to remember that this is always f of 0. That'll equal the y-intercepts. So yeah, you can plug in 0 into your function and get your y-intercept. X-intercepts, on the other hand, I'm just going to write it that way, is where the graph crosses the x-axis. And These ones are a little bit tougher to find because this is when you're looking for where does f of x equal 0. And as we saw in Algebra 2, maybe a little bit in Algebra 1, if you can remember back that far. For some of you guys, that was probably like 7th or 8th grade or something like that. And Algebra 2, the function does not necessarily have to have x-intercept. Okay, you can imagine a parabola, for example, that just has the vertex above the x-axis and opening up like so. It's not going to cross the x-axis. Okay, so yeah, it doesn't necessarily have to have an x-intercept. Does a function always have to have a y-intercept? Well, no, it doesn't necessarily have to do that either. We saw some examples. Oh boy, now my axis is going to be red, so I guess I'll draw the function blue. We saw these functions previously in Algebra 2, the rational functions that had a vertical asymptote. And if you don't remember about those, don't worry, that's a review for next video. Where it doesn't actually cross over the y-axis. So yeah, these are nice points to have, and they're interesting points. And from a calculus standpoint, setting things equal to 0 and finding the zeros of the functions will be a skill that we use quite a bit. But yeah, these are good points to find, but they're not necessarily always going to be there for you. Okay, I think I mentioned at the outset, today's lesson was going to review some families of functions, and we'll have some time in class to talk more if you have more questions about the families of functions. But we also want to really dig into linear functions. And so I wanted to talk about linear models. And so let's really get into linear models. And to do that, if you're following along with your textbook, we're now going to actually go over to page 10, which is where we start the section P2. I'm not going to belabor this too much because I know that you guys are excellent mathematics students. If you weren't, you wouldn't be in calculus. I'm just going to remind you that most of you probably think of the equation y equals mx plus b, which is fine. Okay. But I want to remind you of a couple of other forms for these functions. Okay, this one is slope-intercept. And I like slope-intercept form. It's not that I have anything against it. It's just, if you don't know the y-intercept and all you have are 2 points on the line, or you have the slope and a point somewhere in the xy plane, you know, the probability is pretty low that you're just randomly given the intercept. There's only 1 point out of infinitely many. So sometimes the form that actually is going to work a little better for us in calculus is something called point slope form. And so I want to remind you of what that form looks like right here. In this one, point slope form, okay, you're still given the slope, or you computed the slope. We'll talk about slope calculation in just a second. You know, so that's still one of the parameters that we're going to use. Again, oops, it's right there as well. Okay, the difference is, in this case, slope-intercept form, you had to give the intercept. In other words, you knew the point 0, b existed on the line. Okay, in this one, we actually only know a random point on the line. It just happens to go through x1, y1. That's all we know. This form right here is actually going to prove very useful to you as we get further into calculus. And here's why. A lot of the times in calculus, we're interested in writing the equation of a line, okay, specifically a tangent line to a particular function. The College Board will say, write the equation of the line. But usually all we know is the slope and some random point. So let's say we figured out our slope was a half, and we know it's going through the point 3, 8. Okay, well, if I'm doing this for the College Board, I can write this. I can say y minus 8 equals 1/2. Lost my pen, hold on. 1/2 of x minus 8. Ah, not x minus 8, x minus 3. Get the eraser. There it goes. Get back here. Darn it. And that's a perfectly acceptable answer if all they said was write the equation line. Okay. Where I find it interesting is a lot of my students who are really fixated on slope-intercept form will do this. They say, okay, well, I know the y-intercept, or the y-coordinate is 8. I know the x-coordinate is 3. So this is 8 equals 3/2 plus b. And they'll subtract 3/2 from both sides. And let's see, 8 is 16/2 minus 3 is 13/2. So that has to be what b is. So then they'll rewrite the equation. Y equals 1/2 x plus 13/2. Okay, that's super great, and that's totally fine. What we did here, though, guys, is we created a lot of opportunity for error by going through all of these calculations. And I know you don't think you're going to make that arithmetic error, but in the heat of the moment on the AP exam, this is where some of the silliest little points gets missed. We've all done it. We've all done 2 times 3 and put down 5, right? And it's just that momentary, like, slip, and it can cost you a point on the AP exam. And believe me, you want all the points that you can possibly get. So just a reminder that there are more than one format for equation line, and perhaps your linear model you would want to use is the point slope form instead of slope intercept, so you don't create that opportunity for error. All right, the last thing I want to take a quick moment to talk about is slope. Slope is going to become a very big deal for us as we get working in calculus. So when I teach this class live, I will often say, okay, so tell me about slope. How do you find it? And invariably, one of the first answers is rise over run. And I love that answer because it is so accurate. It's a great way to think about slope in the Cartesian coordinate system. It's perfect, and I will still talk about it in those terms. Then usually some kid will remember that, oh yeah, we had a formula for it. We say, hey, it's y2 minus y1 over x2 minus x1. I'm like, that's great. That's exactly right. I would ask that maybe we also remember that there's a symbol for that difference in y and the difference in x. That triangle is actually the Greek letter delta. And I'm just going to tell you right now, you might as well get used to some Greek letters. If you are at this level of mathematics, then you're probably continuing on, and we start to invoke a lot of Greek letters as we go along. And some of them have very specific meanings. Delta, for example, means change in. So that's what delta is all about. It means the change. So just a reminder that that's how you find your slope, and that's what the delta means when we do it, because those ideas, this idea, especially this idea of slope, is going to turn out to be a very big idea for us down the road. We'll talk about more on slope and different aspects of slope a little bit later, but it does become a pretty big idea for us in calculus, at least the first part of calculus. So, as we talked about last week, we'll be focusing on differential calculus to begin with, and so this becomes a pretty big idea for us. All right, guys, that is everything for our first video today. I'm sure that it's well over 15 minutes and will require some editing down by me, which hopefully I will have done, so you've only been here for 15 minutes. If you have more questions, be sure to check in with your teacher when you guys meet. This one will be either Monday or Tuesday video. So hopefully you had a chance to kind of refresh your brain and get it kicking in some function and linear modes. And we'll see you in class and help you with some examples and do some more work together. All right. Thanks so much for watching, everybody. Have a good one.